This video is going to introduce logarithmic functions. Let's start by reviewing our basic exponential function f of x equals 2 to the x. We've graphed this in previous sections, but we'll repeat the graph quickly here. If I make a table of values, x is negative 2, 2 to the negative 2 is a fourth, 2 to the negative 1 is a half, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4. We can plot these points. So I plotted negative 2 a fourth, negative 1 a half, 0, 1, 1, 2, and 2, 4. And this is the graph of my basic exponential function. It's exponential growth, so it's increasing, has an asymptote of y equals 0. Now, because this exponential function is 1 to 1, it passes the horizontal line test, it must have an inverse function. And to find its inverse, we just switch the x's and y's. So I can create a table of values for the inverse of this function by just taking this table in blue for my exponential function and just flipping the x and the y values. So now when x is a fourth, the inverse is negative 2. When x is a half, y is negative 1, etc. And if I plot these new points, x is a fourth, y is negative 2, x is a half, y is negative 1, 1, 0, 2, 1, and 4, 2, I get the graph of the inverse of my exponential function. So what is this inverse? What is the inverse of f of x equal 2 to the x? Well, to find the inverse of a function, we switch the x's and y's. So I've got the function y equals 2 to the x. If I switch the x's and y's, I get x equals 2 to the y. This expression here, x equals 2 to the y, can be written as y equals log base 2 of x. The logarithm is defined to be the inverse of an exponential function. So x equal 2 to the y is equivalent to y equals log base 2 of x. Notice that when we have a logarithm, the output is now the exponent of our exponential function. So let me give you a more general definition of a logarithm. So a logarithm is defined to be the inverse of an exponential function. So in general, y equals log base b of x is equivalent to the equation b to the y equals x. This is the definition of a logarithm. A logarithm is defined to be the inverse of our exponential function. So a couple things to notice here. Notice that the logarithm always equals the exponent. The base of the exponential is also considered the base of the log. And the thing inside the log is what our exponential equals. So let's do some examples. Let's start by just practicing converting from one form to the other. So I've got two different logarithms. Let's rewrite these in exponential form. So log base 5 of x equals 2. So just jot down my definition again. The definition says log base b of x equals y is equivalent to b to the y equals x. So in exponential form, the base is 5. The logarithm equals the exponent. So 5 to the 2 equals x. In exponential form, this turns into 5 squared equals x. Log base 3 of root 3 equals a half. In exponential form, base is 3. 3 to the 1/2 equals root 3. Base is 3 equals the exponent. So 3 to the 1/2 is root 3. We can also convert into the opposite form. So if we're given an exponential equation, we can rewrite that as a logarithm. So 4 squared equals 16, using my same definition, can be written as the base is 4, so log base 4 of 16 equals 2. Notice that the log equals the exponent. Log base 4 of 16 equals 2. 8 to the third equals 2 can be written as log base a of 2 equals 3. Again, logarithms always equal exponents. Now we have some common logs that come up so frequently that we use slightly different notation. Log base 10 of x is often just written as log of x. If there's no little number after the log, it is implied that it's base 10. So log base 10 of x, we just write as log x. Log base e of x, where e is that natural number, 2.7 something. Log base e is called the natural log, and we abbreviate that as ln. So log base e of x can be written as ln x, and that's our natural log. So now let's practice evaluating these logarithms. And so the key is to remember that you are trying to find the exponent. It helps me to rewrite these in exponential form. So log base 2 of 8 equals what? In exponential form, that's 2 to something equals 8. So we're trying to find the exponent that will turn a 2 into an 8. And the answer is 3. So log base 2 of 8 is 3. The second one, log base 3 of 1/3. So again, we're trying to find the exponent. What exponent will turn a 3 into a 1/3? Well, to move the 3 to the bottom, it's got to be negative, and it has to be -1. So log base 3 of 1/3 is -1. What about log base 4 of 2? So again, we're trying to find the exponent. 4 to what power equals 2? Well, to turn a 4 into a 2, we would have to take the square root of it. Square root of 4 equals 2. And the square root is the exact same thing as the 1/2 power. So 4 to the 1/2 equals 2. That means log base 4 of 2 is a half. Let's do a couple more. Log of 100. This is that common base 10 log. This is asking us 10 to what power equals 100? And the answer is 2. 10 squared is 100. Log base 5 of 1. So finding the exponent. 5 to what power is 1? Well, it has to be 0. The only way we can turn that 5 into a 1 is with an exponent of 0. So log base 5 of 1 is 0. And in fact, because an exponent of 0 always gives us 1, it actually doesn't matter what the base is. Log with any base of 1 is always going to equal 0. Last one, natural log of e. We have to remember natural log means base e. So this is asking us e to what power is e? And the answer to that one is 1. So natural log of e equals 1. All right, let's consider now the graph of log base 2 of x. We actually graphed this at the very beginning of the video, but let's draw that graph again. And the way to get that graph, I think the easiest way is to think about the exponential form. So y equals log base 2 of x means base is 2, 2 to the y equals x. And then we can pick a bunch of numbers for our y values, plug them into our exponential, and get the x value. So I'm really using the fact that my logarithm is the inverse of my exponential. Essentially, it's like I'm creating a table of values for the exponential function and then flipping them, switching the x's and y's to get that logarithm. Okay, so If I plug y equals negative 2 in, 2 to the negative 2 is a fourth. If I plug negative 1 in, 2 to the negative 1 is a half. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. This should be the exact same table of values we got at the very beginning of this video when we started with our exponential function and then we just switched our x's and y's. And so if we plot these points, 1/4 negative 2, a half negative 1, 1 0, 2 1, and 4 2, this is the graph we get in blue. And there's a couple of important features I'd like to point out. This graph has a domain that's 0 to infinity, not including 0. What that means is we can only take the log of positive numbers. That's because our exponential functions have ranges of positive numbers. So logarithms have domains of positive numbers. So we can only take the log of a positive number, whereas the range is actually all real numbers. The graph goes down forever and up forever. This means the outputs we get for logarithms could be positive or negative or 0. This graph has an asymptote. In fact, it has a vertical asymptote at x equals 0. That graph is approaching x equals 0, but it's never actually reaching it. It also has an intercept. It has an x-intercept located at the point 1 0. These features are going to be consistent for a logarithm with any base. So I graphed log base 2 of x, but if we have other bases, we're still going to have that intercept at 1. We're still going to have that asymptote at x equals 0, and the domain will still be positive numbers only. But we can modify these logarithms with graphing transformations. So we can modify our input, we can modify the outputs as well. And so we're going to graph some transformed functions, but before we do, let's go into a little bit more detail about domain. So in the previous example, in this graph, we discovered that we can't take the log of a negative number or 0. The thing that we put inside the log has to be bigger than 0. So in general, if I want to find the domain of a different, more complicated logarithmic function, the idea is I take the thing inside the log, and so in my first example, f of x equals log base 3 of x plus 4. I take the thing inside the log, x plus 4. It has to be positive, has to be bigger than 0. I can solve this for x by minusing the 4, and I get x is bigger than negative 4. In my second example, f of x equals 5 minus ln x. I do the same process. I take the thing inside the log, ignore everything else. In this case, the thing inside the log is just an x. That has to be bigger than 0, and so my domain is 0 to infinity. One way of thinking about this domain, if you like thinking about the graph, in the first example, this x plus 4 takes the graph and shifts it to the left 4 units. And that's why that domain gets shifted over to negative 4 to infinity. Whereas in the second example, there's no horizontal shifts, there's only a vertical shift. Moving the graph up or down doesn't change its domain. Only moving it side to side will change that domain. Okay, but again, it always works to take the thing inside the log, and that has to be bigger than 0. The thing inside the log has to be bigger than 0. So that's how we find the domain of a logarithm. Now let's graph something that has some graphing transformations in it. Let's graph f of x equals log base 3 of x minus 2 plus 1. So this graph has a parent function, or a starting point, of y equals log base 3 of x. The graph of y equals log base 3 of x will have an x-intercept at 1. All of our basic logarithms have an x-intercept at 1. It has an asymptote of x equals 0. And because the base is 3, it's going to go through the point 3, 1. So this is the graph of log base 3 of x in red. Then this x minus 2 inside the parentheses is going to take the graph and shift it to the right 2 units. So I took my x-intercept, I moved it 1, 2 units to the right. I took the point 3, 1, moved it 1, 2 units to the right. My asymptote also moves 2 units to the right. So now I actually have an asymptote at x equal 2. So in blue is the graph of log base 2, or I guess it's log base 3 of x minus 2. Then this plus 1 outside of the logarithm shifts the graph up 1 unit. So I take this graph in blue, I move all of my points up 1 unit. That doesn't change my asymptote, and in purple is my graph. So one thing I notice here is the domain of my transformed function is 2 to infinity. You can also get that by taking the thing inside the log, and it has to be bigger than 0. This horizontal shift changed the domain. The vertical shift did not change the domain. Another thing to notice is we saw that that asymptote moved 2 units to the right. A nice way of getting the asymptote is to look at that horizontal shift. You can actually just take the thing inside the log and set it equal to 0, and that will give you your asymptote as well. All right, that was my last example. I know this was a quick overview of logarithms. We'll continue talking about this concept in the next couple of videos, but please let me know if anything in this video is unclear.